Hello everyone, my name is Rasheed Kibria, PhD student and Graduate Research Institute at University of Florida, at Florida Institute for Cybersecurity Research. This project is my solo project. You can call it as a hobby project of mine because I think all of these projects actually help me in my research in some ways. I quite often do these types of projects, and you see, I have developed one tool here. It is, I can call it as a assembler parser like it, because it is not a totally complete assembler that includes everything from syntax analysis of the provided assembly language code, their debugging, and machine code generation, all of these things. I have only focused on only the machine code generation part. That was my primary focus. So I ignored the syntax analysis and debugger unit design. And this project is actually you can call it assembler parser, which is the main and important thing of assembler in my belief. I strongly believe that it is the main driving force of this assembler, because the whole purpose of this thing is to generate a machine code representation of the provided assembly code, which is specific to some certain processor. I have actually used here Intel 8085 for my model, and you have to write here assembly code in 8085 assembly language, and your code must be syntactically correct. As I have already mentioned, syntax analysis was not my focus, so I ignored it. My tool actually works on your debugged assembly code and converts it to two formats. So one is the OBJ file, the object code file, and other one is the machine code in Intel Hex format. I have kind of ignored this object code because when you have got this machine code in Intel Hex format, then that is sufficient for understanding the code. You can directly upload this machine code into any type of 8085 processor based microprocessor development kit, which are widely available commercially. The main target of my tool is to automate the entire process for assembly language to a machine code conversion. I am not trying to compete with any of the mm, um, um, commercially available assembler tool for 8085. I have implemented this as one of my hobby project, because I really love to think how these assemblers are designed, how they operate, what is the working principle behind them, and all of these stuffs. So let's start on. As you look here, the block diagram, I have identified the part which I am calling it is actually my implementation. You see here the red bounding box. Okay, so first of all, you have to provide some code, some written in this 8085 assembly language, and it should have .asm extension. ASM stands for assembly. If you don't if you forget to put .asm extension with your file format, then it will be actually saved as a text file, but we don't require that. We want that you actually save your assembly code with .asm extension, but your code will be obviously stored in a text file. You just open a text file and write some assembly codes there. Obviously, your code should be purposeful, doing some work like bubble sort, multiplication, division, and adding some bytes like this, or it can be any type of practical applications, just like as you are trying to interface some peripheral circuitry with your 8085 processor like this. So your code should be purposeful to, you should have some certain specific task to do, some major thing to accomplish, all of these things. And most of the important thing here is that your code should be syntactically correct. That means you should avoid by all of these syntaxes of this 8085 assembly language, because this one is the main important task. After your syntax analysis is done, then my tool can come into picture. I have implemented all of these things you have seen. The blocks you are seeing in this red bounding box, I have implemented those with Python, and it can be implemented with basic scripting, just with basic scripting, no requirement for extra library import, or so many extra library import, or so many Python modules calling like this. I just have tried my best to work with my coding skills and all of these things. So just start with this thing. You write some codes in 8085 language, assembly language code in text file. It is first passed through this intermediate code generator tool that was developed by me. I call it as RK intermediate code generator. The main task of this tool is to convert your assembly code into some intermediate representation, because in your assembly language you can use symbolic representations, and also you can use some loop labels, all of these very high level stuffs. There are also some assembly directives like org, origin, eq, equal, db, dw, dot byte, all of these stuffs. So the main task of this intermediate code generator tool is to convert your kind of very high level assembly language code to some intermediate representation for further processing, so that they can be very easily identified. For example, this one of the major tasks of this intermediate code generator tool is to convert your provided all of these symbolic representation from symbolic representation to some important representation that you can actually utilize in later steps by other parts of this tool. I will move to this gradually. So this intermediate representation is nothing but some good and well formatted form of this provided assembly code, and all of these very high level things are gone. That means all of these symbolic variables, the loops, labels, they are converted into some a good format, some understandable format by the later parts of this tool. This is very important because the assembler I have developed, it is actually tries to reduce your code size. Your code may have so many comments. We also need to ignore this because they are not important for our machine code generation. Machine code is nothing but all of these binary, your codes written in binaries, just like as 0 0 1 1 1 1, all of these binary strings like this. And your target is for this tool is to convert all of these things into some machine code into hex format. You can also guess something from this name, that is the hex. It means all of your code should be in hexadecimal format, not in pure binary, because if you want to write this with binary form, then it will be very, very long binary string chain, which is not unreadable for human or debugging purpose. Okay, so then after this intermediate representation of this input assembly code is done, then we will pass this input to object code generator. This object code generator tool is the main thing. I call it the main part of this major project. The intermediate code generator is also very important because it transforms your very high level assembly language code to some good formatted assembly code with proper meaning and very good representation for further analysis. Then object code generator actually operates on this intermediate representation and converts it into some machine code. But this machine code is not in the Intel hex format. It is just kind of something. Some addresses are here, and all of these addresses, there are these machine codes of lines. this machine, there are so many machine codes here line by line, and some addresses and machine codes in the other column like this. This we can call it as object code with .obj extension. Then final step, the linker tool comes, and this linker tool converts this object code into Intel Hex format machine code, which I will try to illustrate in my demo. So this is the main block diagram of my developed tool. All of this has been implemented with Python, and all of these are integrated with only one script. And this script I have written that contains total, I think, 1,400 lines of Python codes. And it actually includes all of these three major parts, that is the intermediate code generator, object code generator, and linker. These three things are the main part of my developed RK8085 assembler parser tool. It is a very, very good parser. I strongly believe it is a very powerful parser because it can handle any type of coding practice you use, which I will illustrate in my demo. So just move for my demo. Okay, so I will first show you the assembly code conversion process of certain of a code that is written in 8085 language code. Here one thing has been shown, one sample file has been shown. It is, this assembly code is targeted to add n bytes of numbers. There are total n number in byte format, that is with only 8-bit numbers. We need to add all of these elements of an array. It actually forms an array, 1D array, and we have to, our main task is to add all of these numbers of this array and store it in some result variable, that is y. Okay, so just look here, it is one provided debugged assembly code. I will not analyze all of these things to you right now, because otherwise the video will be so much long. Just talk about my main focus. My main target is to convert this provided assembly code to Intel Hex format machine code. That is my target, which can be uploaded to any type of 8085 based microprocessor development kit. Here, just you look here, it is well debugged assembly code, because this code satisfies all of the requirements, the syntax requirements, and all of these steps of this thing. And you also look here, there are so many assembler directives, comments here. You see this code is full of comments. For machine code generation, we don't require these comments because they are not valuable for us. They are only valuable for programmers to understand their code if they have a future review on this code. So just look here, there are so many assembler directives like org, db, and eku, all of these things. And you also see here, there are some certain representation for declaring arrays. You declare some variables and put a colon here, then it will be defined as arrays. Otherwise, if you write with only one variable, for example x db, then some certain number, then it will be actually considered as one number only, not an array. For defining an array, you must have to put some variable name and then colon, because it is the syntax of this 8085 assembly language. And org, EQ, DB, all of these are assembler directives. There are so many comments here, unnecessary comments for our machine code generation. We also have to remove those. And my developed intermediate code generator actually deals with all of these things. Now just focus on the main part of this code here. You look here, mvi is a command, lxi is a command, move is a command, dcr is a command, inx is a command. All of these are actually 8085 assembly language command. And you also see here the loops has been declared with labels, and you can actually practice any type of things here. For example, just look at line number 6. I am putting some unnecessary caps between all these two variables, and you also look here, this x variable is actually an array, and it has total 4 numbers, that is 03 in hexadecimal, ech in hexadecimal, and dd 0e, all of these are hexadecimal. But they are, you see here, they are actually declared with 2 lines. I can also write only 1 line for this code. I can include all of these 4 variables with only 1 line, with no spacing, just separated by commas. And my tool should be also be able to handle with this case, because it is from programmer perspective, your code can be any arbitrary look type, can have any type of arbitrary look, but they must be meaningful and they must abide by the 8085 assembly language syntax. So here you see I have put here so many spaces between these 2 numbers, and in the second line, these 2 numbers, there are no spaces between these 2 declarations with only comma. My tool is capable of handling this. And you also look here, you can declare these numbers with any type of format. For example, either byte or decimal or binary or simply a number. If you put write a simply number, for example xdb3, then it will be actually treated as decimal, because the nor if you don't put any extension like capital H or small h or capital B or small b, all of these things, then it will be actually treated as some decimal number. There are total of 4 possibilities, right? The decimal, binary, octal, and hexadecimal. My tool can handle all of these scenarios. I have made my script so much powerful gradually. And you see here, so many high level things are there, the loop labels, all of these things, they need to be converted. If you look here, this again, and JNG again, they need to be converted into some good format, some good format for further analysis by this intermediate code generator tool. The main purpose of this intermediate code generator tool is to do 3 things. First thing is to make your very high level code understandable, analyzable for our further processing units like object code generator and linker. The second task is to remove all of these unnecessary comments from your provided assembly language code. The third task is to identify all of these labels and replace them with some analyzable format for the further processing units. These 3 things are the main goal of this intermediate code generator tool, and it provides the intermediate code representation of this whole entire assembly format in some text format and in some text file, and my later tools operate on this text file and convert it into machine code. This is the main principle here. If you look here at the last line, that is the RST5 signal, this represents your program has been end. Your program ends here, and your microprocessor is being reset, being in reset condition here. There are so many possibilities. There are RST0, RST1, RST2, up to RST7 most probably. My tool can handle all of those things, and also you can write simply halt instruction here, HLT. That also represents the end of this program, the end of this assembly language code. And you know, all of these instructions, That is, I am talking about instructions. Just remember, not about the assembler directives. The assembler directives has no is important, yes, but it is not converted into a machine code directly. But your main instructions like MVI, LXI, move, DCR, INX, they are actually converted into some uh, into machine language code directly. So these are very important to identify which is actually your commands and which are actually your assembler directives, all of these things, because the main purpose of assembler directives is to guide your assembler to have some memory allocation and all of these things, so that they can be called properly by your code. Yeah, that is the main thing. So okay, so I think this is clear to you, the main purpose of my developed tool, that is the RK8085 assembler parser tool. Yeah, now I will actually show the demo. Your code name is uh, add in byte.asm. You can put either asm in capital format or in uppercase or lowercase, it doesn't matter. The main thing is that your file name should be with .asm extension. That is the main part. And just start my tool and see how it works. Okay, I will. This is the entire Python script I have developed. That is very tough to understand and very sophisticated. Total 1,400 lines of codes, I believe. Just to run this, I will press. And one thing needs to be mentioned here, that your code, your all of these assembly codes and your assembler tool must be in the same directory. That is, you create a certain folder in your PC, and in all of those PCs you put my tool, and all of these assembly codes you write. I will actually provide you a demo of 3 codes here to illustrate all of these things. You see here only the assembly extension files are here, no hex file generated. Okay, these are just our source code, and our main target is to generate the hex file in Intel, the machine code in Intel hex format. So just start my tool. I will press F5, then this tool will start to operate, and it is saying you to provide input file name. The first thing I am trying to generate the machine code for this add in byte program. So you write the extension, the name add in byte. Here you can put .asm or not. It is actually optional. You can either put .asm or you can just write like this. No problem. My tool can deal with it. So you put your exact input name and you press enter. Then it is providing you to provide output file name. This is mainly, it has been mainly done if you want to save this output file name with different name. For example, you want to save this output file name as add in byte underscore Kibria, like this. So it can be either same or different, or you can also use the same name. There is also another option provided here. You can just write this extension, this CR in both of these greater and less than sign. Then it will actually take the same input file name as your output file name. Otherwise, the output file name you provide here, it will be treated as your final output file name in with .hex extension. That is the main point here. So I put this and I press enter, and you see your provided code has been successfully assembled, and it is actually done with a very short amount of time. Though it is actually a parser, but I think it is a very good parser because the runtime I think is quite small. So now just move to our folder. Okay, you see this add n byte, this same name with .hex extension has been created, and that is actually holding the machine code with Intel hex format that I will actually illustrate to you. So just open this file. Yeah, this add n byte hex signal has been created, and you see here there are so many lines of codes. Only actually only 4 lines of codes, but your provided input assembly code is 36 lines of code. All of these with so many comments which are unnecessary for our machine code. And if you look here, there is only the main or important tasks, things to be noted here, that because this hex file is very crucial for you to understand. I will now illustrate this Intel hex format. So uh, first of all, you should actually look at the second field. That means this one, this one, this one, and this one. All of these are second fields of your line. When your this second field is 0000, remember all of these things are in hex format. Okay, so you should expect to have certain numbers from 0 to f, 0 1 2 3 up to 9, then a b c d e f. This thing, there are total 16 numbers in this hexadecimal format. No binary string or or very long binary representation has been used. It is mainly done for your for the reader to understand this machine code very clearly. So just move to our main thing. You first look at the second field of each and every line, because they represent the address and in which address these machine codes are stored. Okay, so this C100, if you look at the assembly code, in ORGC100H, we have actually declared some we have allocated this memory to certain variables that is in X, and the memory location is C100H. You can convert it into any decimal or binary format. Okay, one thing I also need to mention here, you don't need to write this address in this hex format. It is not mandatory. You can write it in either decimal, binary, octal, or hexadecimal. There are total 4 options available. That this thing applies for all of these numbers you use. That means you see here, I have actually used MVI B00H. We can also write this with only MVI B, 0. Then 0 will be actually treated as decimal, or you can also put a 0D or 0 capital D or 0 small d. All of these things, they are treated as decimal, right? Only number or number with capital D or number with a small d. All of these things, they are treated as decimal. Or binary, capital B or small b. Hex, capital H or small h. O, that is octal, that is I forgot it, maybe capital O or a small o, like this. Okay, so yeah, just focus on this thing. So this is the memory locations, and after this memory locations you have some data, and the third field here in each and every lines, they actually represent a very important thing. They either represent either they are stored in data or your program has been terminated. There are 2 possible cases, and we can represent those with this 448-bit numbers, that is either 00 or 01. Okay, so 00 means your code, these are actually your code lines, and this actually represents data. Some data has been stored in these memory locations in this RAM. Yeah, you see this hex file, this program code, it will be actually uploaded into your board, and from that board it will actually be stored in some program RAM, and on this program RAM your code, from that program RAM your code will be executed, right? Because we know this memory part, this RAM part of processor is very important, because they actually holds all of this executable data, all of this executable program you are trying to run, right? And for storing this thing, yeah, this RAM is also volatile memory. because once your program is done, then we don't need to store it. We can simply remove this, right? These things are very basic of RAM. Those who have don't understanding of this RAM, just look through some YouTube videos for better understanding. Okay. The main thing is here that either 00 and 01 is possible. 00 means it is their data, and 01 actually stands for your program termination. So if you look here at the last line, we always include this, okay? Because this actually tells the processor that your program has been terminated. This is your last line, and it has a special format, right? I will actually break through all of these things just gradually. Just keep in this thing. 00 stands for data, and 01 stands for your program termination. Okay. Now move to your later three things. Always remember, we will first identify the second column of this line, then third column of this line, all of these lines, and finally the last two columns of all of these lines, right? Because they have some specific meanings. The sixth one, F1, FA, FF, all of these has meanings. What is called? It is basically the checksum of all of these elements in this in a certain line. This checksum concept of Intel is also very very important to understand. I will make it clear to you. Just wait. So okay, so just keep in mind that our last column of all of these lines are actually our checksums. Then what are the numbers between this second this third column and the last column? There, that means 00 and 61, or 00 and F1, 00 FA and 01 FA. There are no elements here actually. So because it is actually the end of this line, and no code is stored here. These represents are actually your machine code. Okay, they can be either coming from direct language, direct your machine assembly instructions like MVI, LXI, ORI, all of these things, or they can be either they can be the data too. Okay, in the first line you see in C100H location, in this memory location we are storing total 4 bytes. 03, EC, DD, and 0E. You look here, the same thing, right? It tells that your data is here. You have declared an ORG statement, and you have allocated memory. Actually, from C100H to C101, C102, C103H. Okay, so these 4 memory locations from C100H to C103H. In these 4 memory locations, they are actually 4 bytes, and they hold all of this data that is represented by this first line. Then what is the first column? Okay, the first column actually represents how many machine codes are in this line. If you look here, there are only 4 machine codes, right? I am also calling the data to be machine code, and also assembly language commands to be machine code, because they are actually translated in Intel hex format in this manner. There are total 4 machine codes, so we will have actually 04, and you must keep in mind that they are in hex format. Then move to our second line. This second line, this the memory location is C00H. Just look here, what is the memory location C00H? From if you look here, in memory location C00H, we have declared one variable and also our code. Okay, we have declared one variable with YEQ C200H. This is actually a memory address, because this EQ is nothing but it represents that it actually tells the assembler that your when you find a Y in your code, you replace that Y with this thing. It can be either a byte or in word that is either 16 bits long or 8 bits long. There are two possibilities. So, okay, in the C00H, in this memory location, we have declared one variable that is C200H, and also we are trying to all of these things, that is MVI, all of these things, and you also see here it is actually EQ statement. In this EQ statement, we don't need to allocate memory for it. So you will not find the declaration of Y here in your hex format. And you also clearly see there are no indication of data like our first line, right? It can be simply changed if you write Y colon DW, then C200H, then your memory will be allocated here. This EQ statement does not allocate memory. It is simply tells the assembler that replace this Y with this number. That is after this EQ statement. And then your code starts. From this, your code starts and it goes up to RST5. And they are also, all of this has been included here, right? From 06002 to this one. And you also see here in Intel hex format, we cannot allow more than 16 bytes in 16 bytes of machine code in a certain line. It is mainly done for user, because user can clearly look at these machine codes and I understand and try to implement those in their development kit. Okay, so this is the main concept. You see the maximum number in one line is 16. That is 10 in hex format, right? And in the second line, you see there are total only 9 numbers, only 9 bytes of our machine code, and that 9 bytes of machine code are here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And the last one is the checksum. I will explain this checksum, just wait. So, and in the last line, you see there are actually no machine code because this one is the checksum part. This one actually represents your program has been ended. There is another indication, the memory location here is 0000. Okay, and here another thing is as there are no machine codes, so the number is 00, and that is also included here. Actually, the fourth line in combined way, this means your program has been terminated here, and your processor stops working at this point when they get this type of thing, because this hex file is directly uploaded to your microprocessor development kit with some programming cables. The processor can do all of these steps on this machine code. Okay, so now I will explain how this checksum is formed. You have got meanings of all of these columns of this line, right? The first column, second column, third column, and last column, they must be first identified. As I have mentioned, the first column, just to have a summary, the first column of all of these lines actually represents the number of machine codes in bytes in a certain line. Okay, then our second column actually includes all of these addresses, all of these memory addresses, and in which memory addresses which codes are stored. Then third thing, they actually represent they are either code is being continued or code has been terminated. Code is being continued when it is 00. If it is 01, then it tells the assembler that it tells the processor that your code has been terminated. The last column is your checksum column. Okay, and the rest of the thing, all of these things that exist between column 4 and between column 3 and last column, they are actually your machine code. In all of these are actually stored in bytes, right? Because 4E, this represents 0100 and 1110, right? Total 8-bit numbers. It is a byte. Okay, now just to explain this checksum, So this checksum is calculated in this manner. You first do summation of all of these elements in a certain line, taking byte by byte. That is, if we look here at the first line, that is 04 C1 00 00 03 EC DD 0E, right? So here you see there are C100. It is actually a word, but we don't need to consider it as a word. We have to convert it in byte format. And after converting it to byte format, we have to summation all of these bytes together. Then we will have some numbers, right? After summation of all the full thing, we will have some certain numbers, but we will only take the 8 numbers, the 8 bits at the lowest level. The result can be either 9-bit, 10-bit, 12-bit, or even more. Okay, so we will take only 8 lowest bits possible. We will by doing this, why we are actually doing, we are actually ignoring the carries, right? We are taking only 8 bits at the lowest level. We are ignoring all of these carries. So after taking this 8-bit number, you make it 2's complement, and that is your result. 2's complement, what it means? You invert the number and add 1 with that. Okay, after that, after all of this conversion, your checksum is available, and I have actually implemented this in algorithm. There are so many functions. There are actually 2 main functions here in my code that actually handles with this thing, with this specific task, that I actually call it as a linker tool. That is the main part of this linker tool, because linker tool converts your object code in some arbitrary format with this Intel Hex format. Yeah, that object code is not actually totally arbitrary. They also have some still structure, because everything is programming is always being structured, like, right? So each and everything should be being structured, some informative for further processes to be done. That is the main beauty of this computer science here. All of these things are structured. So yeah, okay, then we will I have told you the algorithm behind this, right? So you first sum all of the codes in a certain line, including the first thing, how many what is the count of machine code in a certain line. That thing too, 04 C1 00 00 03 EC DT 0E, and similarly the same thing also applies for all of these elements, and also all of these elements. Okay, and then you take the summation, ignore the carries, take only a lowest 8-bit summation result. You convert it into 2's complement, and that is your checksum. This is the logic of this checksum, and Intel Hex format is this. It is very important to understand, because it is the linker, the underlying principle of this linker tool is this. This is a linker tool converts simply your object code from that format to this format. But it is not simple, you believe, because the function is really very tricky, because there are some certain formatting issues. You cannot add more than 16 machine codes in a line, all of these steps, right? They are really very tough to implement, but you can obviously try and implement those. I have actually implemented this in with functions, some complex functions, and later I called that function, because I had to do this thing iteratively. I had to do this quite often. So I to me declaring it by functions, that is very easier for me and for my boss programmer to understand, right? Okay, this is the main thing. So your add invite has been converted to this Intel Hex format. You can upload this to your any MDK and test it, right? Now I will show you another code. This code is mult.asm. Here, if you look here, this code is really a bit complex, and it also covers all types of possible things you can be done. There, first of all, look here. I have declared what GC. There is one comment here, and also comment after some lines. My tool can also handle this, right? This was a little bit tricky, but I have been able to implement this. And you also see this temp num in DW. They are actually being declared with some mixed format, some capital H, small h, capital H, and this one is the decimal. And you also see here, this is declared as a word, but there is no, it is only 8-bit number, 2, 3, H. So the upper 8 bits will be 0, 0, right? 0, 0 in H format, and lower bits will be 2, 3. Sorry, 1, 7. This 2, 3 is in decimal, 1, 7 is in hexadecimal. That is the main thing. And you also look here in DB, we have one space in this between comma and this number. This number is decimal, and this lines is actually joined together. No spacing here. It is a very okay. Yeah, now I recall. Your octal is represented by either capital Q or a small q. I have declared one octal number here, 2, 3 in octal, and that is in this memory location C200H, and these numbers are in memory location C100H. In C300H, use the JDW, you don't put any number here. It represents, it will be actually treated as either 000H, total 16 bit zeros, if that is declared with word. And I am also saying how this word can be represented. It can be either DW or DW or dot word or word. Similar thing applies for DB byte. Okay, and your org can also be replaced by origin. There are so many possibilities. If there are no thing declared here, it will be this memory will be initialized as 0. This is the working principle of this 8085 assembly language. And as I have already mentioned, if you don't put a colon here, it will be treated as only one variable. So this NDB5, it is actually one variable, signifying N is capital N is equals to 5, like this. And org C400H, that is another part, another memory location initialization. And we also here put here two things, num EQ3. As I have already mentioned, this EQ is actually replace all of this num with 3, like this thing. And but this data will not be stored in memory, that is with C400H. And P DW07FFH is another thing. Okay, so just focus on these things. Just focus on the first word statement. Okay. Yeah, here you are declaring so many numbers in a certain array, right? In some certain memory location. So first location that starts with C100H, and it can store only a byte. That means this 9AB2, that will be, it is a word, right? Total 16-bit number. It cannot be stored in this memory directly, because a certain memory location in 8085 processor, it can hold only 8-bit data. So they must be split into two ways, into two parts. One is the upper part and the lower part, and they will be stored in two consecutive memory. In the first memory location, the lower byte will be stored, and in the upper memory location, the upper byte will be stored. That means I am saying here that in the memory location C100H, B2 will be stored, and 9A, it will be stored in C101H in this memory location. In C102H, your data will be F3, and in C103H, your data will be 1A, right? And like this, all of this DW are done. After that, you are again allocating just after this memory location. Then beginning, just let me calculate. There are total 4 variables here. So the end Memory location will be C107H because 4 times 2 is 8. We are there are total 8 bytes stored in this location from C100H to C107H. Then from C108H, our X variable will be stored as an array, right? So in C108H, you will have this 10 by it is C here. It is declared in binary, but it will not be stored in binary. It will be stored in hexadecimal format. Then in the memory location 99, it is in decimal, it will be actually stored as a hexadecimal. The same thing also, if it is hexadecimal, then we don't need to change it. We can simply take this thing. Okay. This memory part actually works like this thing. They are stacked by one after another. The main code starts from what the C00H, and you also see there are so many EQ statements here, and your EQ can also be replaced by equal. You can also use equal instead of EQ. And you also see here there are two possibilities. So I can either directly use colon or without colon. Both of these things must be handled. There are actually so many possible coding practice a certain programmer can utilize. Okay, and you also see again this loop here has been begin, but there are no lines after this. The line is in the next line, and in this loop you have one statement just after this loop level statement. These are again two another coding practices a certain programmer can utilize. And you are also using the levels here, very high level things, and you also trying to do all of these things as you are representing some numbers in either binary, decimal, hexadecimal, or octal format. My tool can also handle this, and you also see here so many spaces after this E command. These practices my tool should be able to handle, and it successfully can handle it after I have invested so many time for it. I really upgraded my program in 3 phases, and I continuously work for 3 days with a very little sleep, because this thing is amazing. I really love this assembler theory. That is, okay, I am working with this thing since my level 4 term 2 at Buet. So since then I am gradually I have understood how this what is the theory inside this assembler, how they actually operate, how they transform some assembly code into machine code, and also having some specific notations or formats like Intel Hex format. And I believe that I will be able to write any code for assembler. My next target is to develop RK8051 assembler, which is mainly targeted for Intel 8051 assembly language programming. Yeah, I am not trying to compete with any of the commercial tools existing. I am only trying to say that if you have that much of passion, you can build your own assembler, right? You can try to do this project by your own and have some. You don't need to necessarily include all of these features that a commercial tool has. You can just focus on the operational part. Okay, so you see here I have only focused on some specific part, right? I have ignored the syntax analyzer part, the debugger part. I am only focusing on the operational part. You can just look here, you can just build your assembler in your own, and that will provide a great fun for you, and it will also try to increase your programming skills and all of these things, because I believe in our world nothing is unpaid. When you are trying to learn anything or trying to understand one thing, you should have some grasp of it, right? You should learn something from it, and in one day there is a very much possibility that your skill can be applied to solve some real problems, right? Because this programming skills really has been able to brush up my programming skills, and it has tried to I have really improved my assembler from a very novice to this expert level, right? So in my first scenario, I couldn't handle these scenarios. Like you declare one loop here, you don't write any statement, and I could not actually handle this scenario. Loop level with one statement directly after this loop statement. I couldn't handle this, but I have developed, improved my assembler to handle this task. So it has become so much powerful and sophisticated. You see, I am trying to, I will now run this and convert it. You look here in my folder, there is only a Mult file. It is actually assemblified if we clear the property .asm extension with a small .asm. Okay, so no hex file has been generated. Now I will run my tool and see if that works here. Okay, your input file name. Now I will put to the same name mult.asm. Okay, or I can also put capital ASM. It doesn't matter. ASM, I put it with ASM extension. Then our output file name, it is asking. Let's say I am trying to store it with different name. Say mult underscore Kibria. Okay. Then I try to run, and it says your provided code has been successfully assembled. Now I move to our folder. You see mult underscore Kibria has been created, right? And its format is hex format. So you declared your output file name to be this name, and you have got this same name, right? This mult underscore Kibria.hex is actually the machine code representation of all of this codes in hex format, in Intel format. Again, you see these there are so many. There is also a certain pattern here, right? They are actually trying to. It is actually the pattern inherent in Intel hex format. They try to categorize all of these codes in various addresses, and that are specified in your original assembly code. C100H, C200H, C300H, C400H, then C00H. You see all of these stuffs here, right? And then your C010, C020, they are just after this some certain memory location adjacent to other thing. They are, so I can call it as nothing but the continuation starting from that machine code, right? Okay, your machine code starts from C00H and it runs up to some certain point, but we don't need to necessarily count what is the start ending point of that code. We can simply write this thing, and you see your last line is this thing, because after this your end statement. This is the end statement of this machine code. So this 7.6, that is actually stands for this halt signal. And again, this end is actually used in assembly language code, because your assembly code can have multiple halt statement, but you don't need to stop the function of this assembler at that string. Your assembler should do still translating. It should not stop when it encounters first HLT instruction. You don't want that. So this end, this is the main point for using this end statement. And again, this end is actually an assembler directive. It will not be translated into some effective machine code, as you are clearly seeing here. This last numbers I have already mentioned. They are your checksums. This thing is the count of the machine code in a certain line. There are 0B. It is actually 11, right? So there are total 11 machine codes. One, just to focus on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So there are total 11 machine codes in bytes, and this is the count, and the last one is the checksum. You can just verify this with your calculator and try to think. It was really very tricky for me to implement this linker too. Okay, that is not so much easy, but you can really build your own if you have that much of passion and interest. So you can directly upload this mult format, this mult underscore Kibria dot hex file to any type of 8085 based microprocessor board. Okay, so these are the two codes. The third code I want to show you, it is the bubble sort code. This assembly file is quite big. You see there are total 65 lines of code. Is it possible for human to translate all of these things to machine code manually? Obviously no. Who will spend so much time? There are so many levels, so many things, so many high level things, so many comments. It was the main motivation for my development of this RK8085 based assembler. That is the main thing. You also see here is again various types of coding practice has been used. There are this DB has been separated into 2 lines. Okay, but they are actually they can be they are actually forming a 1D array of a certain of this variable x. This x holds 04h, 33h, 22h, 4411. All of these are in hexadecimal format, right? So again, another origin org address. This code is mainly targeted for the 80 based board I bought recently. That is the 199 USD. You can easily order it from eBay. It is widely available. It comes from India, so you can order this and get it. I have a recently my RK lab is growing with so many assemblers, these microprocessor boards, the FPGA board, because I am very enthusiastic in electronics and hardware security steps. So my research is actually on hardware security, and I am working on RTL security. That is a really very challenging and very emerging field. So yeah, I have a quite fashion, very. I really like so much to work with electronics and all of these stuff. So these are my hobby from my undergraduate level at BUET. Okay, so and I will now run this and transform this. Again, you look here, no hex code has been generated for bub SRT2 file, the bubble sort file. Okay, I will run my tool and figure out whether it works or not. Okay, the file name is bubsrt2 dot. Okay, I will not put any extension here. I will just press enter. Then our output file name. You can again write bubsrt2, the same file name, or you can just write this cr. Then this cr will automatically take your input file name as your output file name. I just write this and press enter, and yeah, again see your provided code has been successfully assembled. And now you will look here. Yeah, bub SRT2, that hex file has been generated, and this one is the machine code representation of this thing. You see, my tool can handle any type of thing, and you will be very amazed to know that my tool can operate on all the on the entire 8085 instruction set, and that instruction set consists of total 246 instructions. That is not an easy task. Okay, that is not an easy task at all. There are so many commands and so many types I had to deal with, but I have been really successful. It is I am very pleased to let you know. Okay, so this one is it was all from me today. It was the demo of my RK8085 assembler. I will now focus on my next hobby project, that is 8051 based assembler. So I will encourage you to develop this type of assembler by your own. Why? Depending on commercial tools. So when you can automate the entire process by yourself. Okay, this was the main motivation. You don't need to include all of the steps. You just include the operational steps, and you will be very good to go. Okay, yeah, this one. This one is the main motivation. Okay, so I hope you have enjoyed my demo. If you have any questions, please feel free to ask. Okay, thank you.